This is a video from section 9.3. The directions say to solve the differential equation. Let's start with number 1. It says dy dx is equal to 3x squared y squared. And in the first case, I'm going to assume y does not equal 0. Now, this is a classic separable differential equation. And so we want to literally separate the variables. And so in the first step, I'm going to divide both sides by y squared. So 1 over y squared dy dx is the same as 3x squared. And so 1 over y squared dy is the same as 3x squared dx. Okay. Now, let's rewrite that on the next page. 1 over y squared dy is the same as 3x squared dx. And now I want to integrate both sides. So the integral of 1 over y squared dy is the same as the integral of 3x squared dx. Now, this says the integral of y to the negative 2 dy is the same as the integral of 3x squared dx. Right? But recall, the integral of x to the n dx is 1 over n plus 1 x to the n plus 1 plus c. And remember, n cannot be negative 1. And so we get y to the negative 1, right? Because negative 2 plus 1 is negative 1 over negative 1 is equal to 3 times 1/3 x cubed. 2 plus 1 is 3 plus c. I hope that's okay. And so therefore, negative 1 over y is the same as x cubed plus c. And if you don't mind, I'm going to put that over 1. And so therefore y is negative 1 over x cubed plus c. So I just went ahead and solved for y. Now, if you look, in this case, I assume y does not equal to 0. Because then I wouldn't be able to integrate 1 over y squared dy. But the complete solution here, okay, the answer here is y equals negative 1 over x cubed plus c and y equals 0. Now, why does y equal 0 work? Because if I take the derivative of y with respect to x, I get 0, and that really is equal to 3x squared times y squared, but remember y is 0. And so it does work. So that's how we do problem number 1. If we take a look at problem number 3, suppose dy dx is equal to x times the square root of y. And again, in this case, I'm going to assume that y does not equal 0. Okay? And so I'm going to divide both sides by square root of y. So 1 over square root of y dy is the same as x dx, like this. And so I'm going to integrate both sides. So the integral of 1 over square root of y dy is the same as the integral of x dx. And so the integral of y to the negative 1/2, right, dy, is the integral of x dx. And so here, I get y to the 1/2 divided by 1/2 is equal to, now the integral of x dx will just be 1/2 x squared plus some constant c. Now, when you divide by 1/2, that's the same as multiplying by 2. So 2y to the 1/2 is 1/2 x squared plus some constant c. And I'm going to divide both sides by 2 to isolate y to the 1/2. So y to the 1/2 is 1/4 x squared plus some constant k, where k is equal to c over 2. Now, if I square both sides, I solve for y. So y will be 1/4 x squared plus k raised to the second power. And so the answer here will be y equals 1/4 x squared plus k to the second, and then y equals 0. Because y equals 0, again, still works for as a solution to this differential equation. And that's problem number 3. So let's go ahead and take a look at problem number 5. Suppose x times y prime equals x squared plus 1. So xy dy dx is equal to x squared plus 1. And what I want to do first is I want to divide both sides by x. And so y dy dx is equal to x squared plus 1 divided by x. And so y dy is equal to x squared plus 1 divided by x dx. And so I'm going to split the fraction, and I get y dy is equal to x squared divided by x plus 1 over x dx. And so y dy is x plus 1 over x dx. And from here, I want to integrate both sides. So the integral of y dy is the integral of x plus 1 over x dx. Now, from here, 1/2 y squared is equal to 1/2 x squared plus natural log of the absolute value of x plus c. Remember, the integral of 1 over x dx is natural log of the absolute value of x plus c. So we have to add the c at the end. And so y squared, I'm multiplying both sides by 2, is x squared plus 2 times the natural log of the absolute value of x plus k, where k equals 2c. Now, if I solve for y, I get plus or minus the square root of x squared plus 2 times the natural log of the absolute value of x plus k. And that's problem 5. Let's take a look at problem number 7. Suppose e to the y minus 1 y prime is equal to 2 plus cosine x. So e to the y minus 1 dy dx is equal to 2 plus cosine x. And so, therefore, e to the y minus 1 dy is equal to 2 plus cosine x dx. And now I need to integrate both sides. So the integral of e to the y minus 1 dy is the same as the integral of 2 plus cosine x dx. And we're almost done. So let's rewrite this over here. The integral of e to the y minus 1 dy is the same as the integral of 2 plus cosine x dx. And so the integral of e to the y dy is e to the y. The integral of 1 dy is y, so we get e to the y minus y on the left side. And on the right side, we get 2x plus sine x plus some constant c. And we're done, right? Because we have e to the y minus y is equal to some stuff. If I just had e to the y, it would be a bit easier to solve for y. And of course, if I just had the y here with no e to the y, that would be okay to solve for y. But when you have e to the y minus y those two terms put together, it's much harder to solve for y. So you would be finished once you get to here. So let's take a look at number 9. So here we have dp dt is equal to t squared p minus p plus t squared minus 1. So dp dt is equal to t squared p minus p times 1 plus 1 times t squared minus 1. There's a hidden 1 there because I want you to notice there's a p in the first term and the p in the second term. So we're going to take that out. So dp dt is p times t squared minus 1 plus 1 times t squared minus 1. And so dp dt, so we just did a little factor by grouping here. So dp dt is t squared minus 1 times p plus 1. Now, 1 over p plus 1 dp dt, right, is equal to t squared minus 1. And so 1 over p plus 1 dp is equal to t squared minus 1 dt. And I want to integrate both sides. So the integral of 1 over p plus 1 dp is the same as the integral of t squared minus 1 dt. And so natural log of the absolute value of p plus 1 is equal to 1/3 t to the third minus t plus c. So I hope that's okay. Now, so let's write that over here. Natural log of the absolute value of p, let's go back, p plus 1 is equal to 1/3 t cubed minus t plus c. Now, the absolute value of p plus 1 is equal to e raised to the 1/3 t to the third minus t plus c. Okay? Now, what this says is p plus 1 is plus or minus. Now, I'm going to rewrite this term as e to the c times e to the 1/3 t cubed minus t. The hardest part about this problem is not so much the integration, it's how to solve for p. All right? Now, I'm going to let a equal plus or minus e to the c. And so p plus 1 is a e to the 1/3 t cubed minus t. And if I solve for p, I'm finished. P is -1 plus a e to the 1/3 t to the third minus t. And that's how we do problem number. So this is problem 9. And we're going to take a look now at problem number 11. And so on problem 11, we have d theta dt is equal to t secant theta divided by theta e to the t squared. Like this. Now, I'm going to cross multiply, and I'm going to get theta e to the t squared d theta is equal to t secant theta dt. But we want the variable t on one side, and we want the variable theta on the other side. And so theta e to the t squared divided by secant theta d theta is equal to t dt. And now I'm going to divide both sides by e to the t squared. And also don't forget 1 over secant theta is equal to cosine theta, right? And so theta cosine theta d theta is equal to t divided by e to the t squared dt. And so theta cosine theta d theta is t e to the negative t squared dt. And we want to integrate both sides. Now, let's start with theta cosine theta d theta. So we're going to integrate the left side and the right side separately, and then we're going to put everything together at the end. Now, I'm going to let u be theta, and I'm going to let dv be cosine theta d theta. So this is called integration by parts, and I'm doing it the traditional way. There's another method called tabular integration, but not all instructors are warm to that, so I'll just do it traditionally where instructors should be okay with this method. Now, if I let u be theta, du is d theta, and if dv is cosine theta d theta, v is equal to sine theta. And so the integral of theta cosine theta d theta is theta sine theta minus the integral of sine theta d theta, which is theta sine theta plus cosine theta, and we'll call this constant C1. Okay? Now that's the left side. If we take a look at the right side, we get te to the negative t squared dt. and I'm going to let u be negative t squared. Du is negative 2t dt. And so t dt is negative 1/2 du, right? And so t dt is negative 1/2 du. So negative 1/2 the integral of e to the u du is what you should come up with when we make our substitution. And so this is negative 1/2. The antiderivative of e to the u is e to the u, so we get negative 1/2 e to the u plus, we'll call it c2. And so this is negative 1/2 e to the negative t squared plus c2. And we now get to put everything together. So this is what we have. We have the integral of theta cosine theta d theta is equal to the integral of t e to the negative t squared dt. Now, we integrated theta cosine theta d theta first and got theta sine theta plus cosine theta. So we get theta sine theta plus cosine theta. That's the left side. And on the right side, we get, what do we get? We get negative 1/2 e to the negative t squared plus some constant k. And again, it always depends on your instructor, but this would be pretty good if you got to this stage. And that's going to conclude this video for section 9.3. And we worked problems 1, 3, 5, 7, 9, and 11. Thank you.